you would like to ask? Or can I go back to 2.4? So in 2.4, I wanted to show you a numerical example, and I also wanted to show you another linear limit with a precise definition of the limit epsilon delta. Okay. So I don't remember exactly which problem we did, but I don't think we did problem 20 on page 117, which is limit as x approaches, I think it says 10. Yes, it says 10. And 3 minus 4/5 x equals 1. And so I copied it from here. And it says, prove this statement using the epsilon delta definition of a limit. And I just picked this one. Okay. So first of all, I will plug it in and make sure that it's 1. Is it 1? So 4/5 times 10 over 1. 4/5 times 10 over 1 is 8. 3 minus 8. Is it 8? I didn't copy something here. Oh, I'm sorry. I copied from a different problem. So it's -5, of course. Sorry about that. I don't know how I came up with 1. So 3 minus 4/5 x equals -5. But I think I looked at that instead somehow. Sorry about that. That's why we plug in, and that's why we check. Because you never know. Okay. I'll check again. So 3 minus 8 is -5. True. So now the requirement is to write the definition. So this is equivalent both directions with saying that for every, can anyone help? For every, yes, indeed, epsilon greater than 0. Awesome. There exists, I will find a delta, what type of number?
Greater than 0.
Very good. Such that what? When we pick, what is this, by the way? X minus, what is A in our situation? 10. Less than delta. F of this x, which is the function, 3 minus 4/5 x minus -5, which is plus 5, will be less than epsilon. But by the way, why do I need this?
Can't be 0.
Exactly. Because we know that the absolute value is greater than 0. But this guarantees that you do not pick x to be 10. Good. So that's a definition. And we have 2 steps. We have to try to prove each direction. Okay, I'm going to write the second half of the proof. It doesn't. Yeah, I don't ask you to do anything. I just want you to say that show that delta found in step 1 works by reversing the steps from part 1. That's all I need you to say in part 2. Nothing else. You don't need to do anything. I just want you to say that show that delta works, whatever we find, by reversing the steps from part 1. That's it. But now let's focus on part 1 because we haven't determined delta. So part 1 is right here. Where is the starting point? Where is the starting point? But I have to determine this. So the starting point is here, at the end. So the absolute value, can anyone tell us what to do in here? -4/5 x, 3 plus 8 plus 5 is 8, less than epsilon. Then can anyone tell us how to continue? We can stop before we get something like this in absolute value. I have to continue till I get x minus 10 in absolute value. So what would you recommend we do next? Find the least common denominator, which is good. So then the numerator of this fraction needs what? Yes, of course. So then negative 4x plus 40. Very good. Great job so far. Now, the next step would be, very good, top and bottom. That's all I can do for now. Good. Then, good steps. Correct steps. Next. We do what at the top? Factor out negative. Because remember, I'm after x minus 10. So negative 4 in parentheses. Do not take it out of the absolute value yet. You cannot do that. We cannot do that just yet. In parentheses. Correct. Now we split the product. Of course, I don't have to write the absolute value 5. I can directly write 5. That's very clear. Good. Now let's split the top using the property of the absolute value. What do I write? Negative 4, awesome, times the absolute value of, very good, awesome. How much is the absolute value of negative 4? Very good. We're very close. And now I only want the absolute value on the left-hand side and nothing else. Multiply both sides by 5/4. So the absolute value of x minus 10 less than 5 epsilon over 4. Now please connect the dots. Compare this to this. And tell me what is delta. Exactly. Therefore, delta must be 5 epsilon over 4. So in other words, if I give you epsilon as 0.1, you can calculate delta. If I give you epsilon as 0.2, then you can calculate the corresponding delta, and so on and so forth. Why? Because the limit exists. I'd like to finish this unless you have questions for me, please. Any questions? Anything? I'd like to finish it with a numerical example. So on the same page, 117, I'd like to show the mechanism. If we have the epsilon, and you'll tell me in a minute what it is, which is the delta that we have to pick. So this is a perfect example in which we are given epsilon. We do not have to show or prove anything. We're only asked to find the corresponding delta. For this specific epsilon that we have in the problem, find the corresponding delta. Okay, ready? Okay, so let me copy this. So this is problem 3 on page 117. And this is what they're giving us. They're giving us a function that is the square root of x. That's the function. And somehow my markers are got under my book. and they are giving us 2, of course, and 4. And this point is 2.4. This point is 1.6. And they want us to determine the corresponding delta. Okay, so we know that every time we pick x minus x close to 4, this is our A, and this is our L. So less than delta. This will always imply, can anyone give us the second half? The absolute value of, what is the function here? Very good. Minus the limit. What is the limit here? 2. Less than, how much is epsilon in this case? It's a numerical situation. Can anyone give us epsilon?
0.4.
Do you all agree with 0.4? Because this is 0.4 and this is 0.4. So epsilon must be 0.4. Very good. Like before, where do we start? We want to find delta. Where is my starting point? Identical with the previous situation. It's just that that one didn't have epsilon 0.4. It just had epsilon, but not 0.4. So, where is our starting point? Identical with the previous example. Where will I start? I cannot start here because I don't have delta. So I must start where? Very good. So I have this square root of x minus 2 less than 0.4. This is an absolute value inequality. I need to solve this inequality to get delta. So can anyone tell us how to solve this inequality? Say it again. No. Very good idea, but there is no fraction here. I cannot, yeah. And it's absolute value, so I have a difficulty with that. So let me refresh your memory. The absolute value of x less than 3. What does this mean? We're trying to find x values whose distance from x to 0 is 3 units. Where will I find those numbers?
In between.
In between?
-3.
-3 and 3, of course. Thank you. In the same way, we have to solve this. So can anyone give us an idea what to write next? So this was just an example. -0.4 less than very good, less than excellent, very good. So in order for us to get to delta, we have to solve this inequality first. Solving this inequality will give us delta eventually. Good. What will be the next step? I need to solve for x. What do I want to get rid of now?
Add 2.
Of course, I need to get rid of 2. So I'm adding 2 to all three sides. 1.6 less than the square root of x less than 2.4. Good. Now, I will never ever say that this is a legitimate operation in general, what I'm going to do next. However, because these are all positive numbers and they are ascending from the smallest to the largest in this situation, I am allowed to square all three sides. I'm not going to ever say that this is a legitimate operation otherwise for any x. But now, because I know x is between these two positive numbers, I will square all three sides. Oops. I will square the left-hand side, I get 1.6 squared. I will square the middle, and I will get x. And I will square the right-hand side, and I get 2.4 squared. So when I 2.56 less than x less than 2.4 squared, that is 576. Okay, good. So then I'm looking back. Am I there yet? No, I'm not there yet. I need to construct this, but I only have x. So what should I do to all three sides to get the x minus 4 in the middle? Of course, I want to subtract 4 from all three sides. So 2.56 minus 4, x minus 4, and 5.76 minus 4. In the middle, I have x minus 4. On the right-hand side, I have 1.76. And here I have negative 1. What is it? 44? Correct me if I'm wrong. Are you with me so far? And now the question is, fine, it looks awesome, but what is it? What is this? Here's what it is. There are two options. One option will be to consider x minus 4 in absolute value less than 1.76. And the other one, x minus 4 in absolute value less than 1.44. And I know you're wondering, listen, how did you come up with this? Here's how I came up with it. Because I know that this situation represents negative 1.76 less than x minus 4 less than 1.76. This is what we just discussed. This one means negative 1.44 less than x minus 4 less than 1.44. Why? How do I know? Because that's exactly what it means. It's this. Same concept. But I have to decide now between this to be delta and this to be delta. I go back to the drawing. My drawing is not perfect, right? But I know for sure that if I choose the smallest, I am fine. If I choose the biggest, this, I may not be fine. By choosing x here, I'll be okay. But by choosing x here, I will not be okay. This f of x will fall outside of the interval. So I know for sure that I have to choose the smallest of the two. So which one is the smallest of the two? Is delta going to be 1.76 or is delta going to be 1.44? Yes. No. So the distance between the x value I pick and 4 cannot exceed 1.44. So delta is 1.44. Any questions? As you see, the numerical example is a little bit more difficult than the precise definition. Why? Because I have to be able to solve this. Okay, once I'm able to solve it, then I have to realize that in the middle I have to have the x minus 4. And then I have to change it back into an absolute value inequality in which I have to decide which one is, it has to be the minimum of these two. And the minimum is 1.44. Any questions for me? Any questions? You may encounter something like this in WebAssign. I am hoping that you are finished I did not get the chance to look at WebAssign today, and I need to change something. So you have more than one option for this skills assessment if you want to go back and resubmit it, because I'm going to change it. Ella told me that it's just one submission. I'll change it. Any questions? You can go back and increase your grade if you want to. Anything else from me? We decided to have our first test, and I'm looking now at the calendar, and I hope you check the calendar. It's right here. And I think I scheduled it tentatively, of course. We will discuss and agree upon it. So let me see. So the test should be a week from Wednesday. Well, we have to wait and see, because I always review at least an hour, complete hour, just review of a test. So we'll see. I still have sections 2.5, 2.6, 2.7, and 2.8. So I may have to reschedule that a little bit down the road, another week probably. We'll see. I just want you to know that. Any questions for me? So everything 2.1 through 2.4 should be finished between now and Wednesday, so you can ask questions on Wednesday. No more extensions. That's it. 2.1 through 2.4, please. Now, if something is wrong and you need more help and you need extra time, I will give it, but please attempt those problems. Any questions? Okay, 2.5, famous continuity. Why is it famous? It's because it's a very important topic. And the swapping of those operators requests or is possible only if the functions are continuous. Function or functions. Okay. I would like to so list first of all in how many ways a function is discontinuous. Okay, so discontinuity first. First, discontinuity. Okay, here's a possibility. At x equals a, of course. What type of discontinuity is this?
Jump.
Very good. We call it jump. Jump discontinuity. And here's another. What type of discontinuity is this? Infinite discontinuity, right. Infinite discontinuity. And here's another. What type of discontinuity is this? Removable. This is the only one, the only situation in which I can, by making a minor change to this function, I can make it continuous. There is nothing I can do here ever. There is nothing I can do here ever. But here I have the option of making this function continuous. All I have to do, only because the limits from the left and from the right are the same. So here, the limit as x approaches a from the left of f of x equals the limit of f of x as x approaches a from the right. This is the condition for a removable discontinuity, as you see, left and right. So then a function is continuous if I can draw the entire graph without lifting the marker off the paper or the pencil off the paper. So this will be a continuous function. I graph the entire graph without lifting the marker off the paper. So this function is continuous. Okay. So then, the next step I would like to write is continuity at a point. At a point. So a function is continuous at a point. Let's come back to the removable for a second. So the function will be continuous at this point if the limit from the left and the limit from the right, and what else has to be the same?
To be continuous?
Yes.
It has to equal the value of the function.
Exactly. That's the correct answer. Very good. So limit as x approaches a from the left of the function must equal the limit of the function as x approaches a from the right, and must equal the function value at that point. If a function is continuous at a point, the function has to have limits from left and right, and those limits have to exist, have to be a number, and they have to equal the function value at that point. Mandatory. What about a function being continuous on an interval? Function continuous on an interval. If it is continuous at, when is a function continuous on an interval?
Every point.
At every point on that interval. Another important concept. All functions are, I shouldn't say all, I should list, just to be specific. So functions like polynomial, rational, because you can say, what about a piecewise defined function? I don't know, I can't. So I should not just generalize and say all functions like that. Polynomial, rational, radical, trig, and I can say etc. are all continuous on their domain. These are all functions that are continuous on their domain. Also, any combination, sum, difference, product, division, of continuous functions is, or any combination, the sum, difference, product, division of continuous functions is, if I add two continuous functions, I get a new function that is continuous. If I subtract two continuous functions, I get a new function that is continuous. If I multiply or divide two continuous functions, I get another continuous function. Okay. I would like us to, and here is the swapping of the operators. We're not using it today. It's used for something else, but this is the theorem that I keep telling you about, moving or swapping the operators. Here it is. If f is a continuous function at b, it looks complicated. It looks complicated. You'll see when we get to apply it. And f of g, and limit as g of x as x approaches a is b, then the limit of f of g of x is f of b. In other words, so if you forget that, here's what happens. Limit of f of g, f and the limit swapped, are getting swapped. F is outside and the limit inside. The same thing with the limit of the square root of x is the square root of the limit of x. So the function, which is an operator, and the limit, which is another operator, got swapped because of the conditions of continuity being fulfilled, right? So here an example. So limit of the square root of x squared plus 3 as x approaches 1 is the same with the square root of the limit of x squared plus 3 as x approaches 1. We swapped the operators. This function, which is an operator, the square root, and this, which is an operator, they got swapped. Why? Because x squared plus 3 is continuous. And the square root is continuous. Not just x squared plus 3 is continuous everywhere, but also the square root of x squared plus 3 as a function is continuous everywhere. So that allowed us to swap the limit operator with a square root operator. And that's the theorem that I keep telling you about. Any questions? Any questions? Okay, so I'd like us to, and also we're going to talk about the intermediate value theorem in a minute. I'd like us to look at another piecewise defined function, graph it, and answer what they're asking us to in the problem. So it says find the numbers at which f is discontinuous. At which of these numbers f is continuous from the right, from the left, or neither? So before we do that, let me discuss continuity from the left and from the right. We can go back to any of the graphs. This function is continuous from the right or from the left? It's continuous from the right because the function value, the limit, equal the function value from the right. The function value, the limit from the function as x approaches a from the right equals the function value at that point. It's not continuous from the left because the limit from the left does not equal the function value. So that's a definition of continuity from the left or from the right. So this function I meant this open. So limit as x approaches a from the left of f of x equals f of a, which means continuity from the left. Continuity from the left. Any questions? The same thing for continuity from the right. So let's choose a problem. So it's asking us to find where it's continuous and where it's discontinuous, and if it is continuous from the right, from the left, or none of the above. And sketch the graph, of course. So we have three piecewise defined functions. We can choose any. And then I would like to talk about the intermediate value theorem. Any preference?
42.
We want to look at 42. Very good. So let's look at 42 on page 129. And that is f of x. It has three branches. It's a piecewise defined function. We're asked to graph this function and then answer a few questions. Ready? As we did before, I would like to change this into an interval, and this into an interval. So we can identify the parentheses, the brackets, exactly as we did before. And remember, I don't want you to change anything if it works. So if you have a different method and you don't consider mine easier, stick with your own. Okay, so what is the interval for this? Can anyone give us the interval notation for this? I know you know. Isn't this negative infinity to 1? Can anyone give us the interval notation for this? Very good, with parentheses. And for this one, 3 to infinity. I need to identify the domain. I can't move on to anything, to any step before I identify the domain. And the domain of this function is negative infinity to positive infinity. Do you all agree? 1 is here, 1 is not here, 3 is not here, but 3 is here, and everything else. There is no gap in the domain. So indeed, all real numbers. Perfect. So now we need a table of ordered pairs. And please tell me which key x values I cannot skip or omit for sure. 1 and, yes, 1, 0, and 3, but specifically 1 and 3. The reason why I changed the into interval notation is because I want you to see where I'm copying these symbols from. Bracket to the left, parenthesis to the right, exactly under 1, and they are touching. The same thing, but parenthesis to the left and bracket to the right, and they are touching under 3. Now I know it's an overkill, but I'd like you to dictate what is the first branch, or the branch that goes to, I shouldn't say the first, I should say the branch that goes from negative infinity to 1. Correct. Very good. Awesome. From 1 to 3, 1 over x. And from 3 to infinity, right, that's obvious. Good. So now we have to plug in some numbers in each that I need to plot, right? Some ordered pairs. So I'm going to plug in negative 1. And please give me the answer. Perfect. Please plug in 1 and give me the answer. Good. Please plug in 1 and you should know, don't do that. But I get 1, I have to. Plug in 0. Okay. Oh, so that's why. That's why. I'm sorry. Sorry. My apologies. I should pay attention to what I'm doing. It's definitely indicated and advised. So 1. Good. So 1, and then let's plug in 3. Of course, negative 1, 0, 1. I just put it in without thinking, because I wanted it in the middle, but 1 and 3 should have been to the right. Okay, so my apologies, my mistake. So plug it in 3. Please put these numbers right inside the parentheses so you don't make a mistake, and then plug in 3. Very good. From left to right, please give me the first ordered pair. Very good. Negative 1, 0. Awesome. Next ordered pair. 0, 1. And then the next ordered pair is 1, 2. Full point or open? That's why I put the bracket.
Oh, yeah.
So it must be closed, right? Good. So we finish with the first branch, and no one can extend it anywhere. Okay, the next one, 1, 1. What type of point is that? Very good, awesome. And then 1/3 at 3, which is an open point as well. And I don't know if you remember, we graphed this function before, 1 over x. You must remember this graph. Please remember the graph of 1 over x. So then this is the piece in question. And now finally we get to 3, 0, which is this point. And let's say 4 and 1. Let's make 1 more. We need that. So here's the graph. So this is the graph of function f of x. How will you answer concerning continuity? Is this function continuous everywhere? No. So it's discontinuous at you can see it here. 1, the left-hand side is 2 and 1. It doesn't have a limit there. And the right-hand and 3, 1/3, 1 and 0, so it doesn't have a limit there, right? So x equals 1 and x equals 3. So points of discontinuity at 1 and 3. Do we agree with that? Yes? Okay. Now let's look at what happens at 1. Is the function continuous from the left or from the right, or none of the above? From the left, because limit as x approaches 1 from the left of f of x equals f of 1. Continuous from the left. Do we agree with this? Okay, what about 3? What will you say about 3 at x equals 3? Correct. Very good. So limit as x approaches 3 from the right of f of x equals f of 3. And this is continuity from the right. So this was another example of the piecewise defined function. We had a couple before. Any questions? Any questions? Okay, I would like to look at this problem 45 before we talk about the intermediate value theorem. So let's see what it's asking us to do. For what value of the constant c is the function f continuous on all real numbers? And we are given a function, and it has, we call a parameter c in the function exists, and we want to find the values of constant c, or value, or values, I don't know, we'll see, so that the function is continuous everywhere. Ready? Okay, so let's take a look. So this is problem 45 on page 129. We have f of x equals cx squared plus 2x for less than 2, and x cubed minus cx for x greater than or equal to 2. I think it's c cubed. Yes, it is. Okay. What can you tell me about cx squared, a constant times x squared plus 2x? Do you think that this function is continuous? Forget about the rest. I'm only asking about this one. Do you think that a constant, 5x squared plus 2x, is it continuous everywhere? Yes, because it's a polynomial function. Not just on less than 2, anywhere. A number x squared plus 2x. Continuous everywhere because it's a continuous function. It's a polynomial function. Okay. What can you tell me about x cubed minus cx? Is that continuous? What type of function is it? Yes, still polynomial. Perfect. Is it continuous? Yes. If you remember, we wrote this note a few minutes ago in which we said polynomial functions are continuous everywhere. The domain is everything, so they are always continuous. So this is my starting point in analyzing this function. I have to write first that cx squared plus 2x and x cubed minus cx are continuous as what? As are continuous as what did we just say? What are they? As polynomial functions. As polynomial functions, which are continuous everywhere, and we know that. Perfect. The question is continuity at x equals 2. That's the question. what has to happen at x equals 2 for this function to be continuous there? The limit as x approaches 2 from the left. Which function do I put? 2 from the left. Very good. Cx squared plus 2x must equal the limit as x approaches 2 from the right. From which function? Minus cx. And this must equal the function value at 2. If all three are fulfilled, all three conditions are fulfilled, and they're all the same, they all exist, and they're all the same, then the function will be continuous everywhere. Can anyone give us this limit? As x approaches 2 from the left of cx squared plus 2x. What will that equal to? X approaches 2.
4c.
4c, very good. Plus?
4.
Plus 4. 4c plus 4 must equal. Can anyone give us this limit? Yes, 8 minus 2c. 2c. And now can anyone give us f of 2? Which branch are we going to use for f of 2? Because only one is allowed. Exactly. So that will be 8 minus 2c. Of course, this is redundant. You can say, well, you wrote it twice. It's the same thing. You're right. So I do have this equation. What do you think I'm going to do? What is the only thing I can do here? Solve for? Yes, solve for c, and that's exactly what I want to find. So I will be, let me write it one more time. 4c plus 4 equals 8 minus 2c. I will move c to the term with c to the left and free term to the right. So then I have 6c equals 4. So therefore c is 4 over 6, or 2/3. Now I can write the function. I go back and I copy everything, but I replace c. So I have 2/3 x squared plus 2x. And I have x cubed minus 2/3 x. Question for you. Do you think that this function is continuous everywhere? What do you think? Of course, we made it continuous everywhere. It was continuous everywhere on less than 2. It was continuous everywhere on greater than 2. And by determining the appropriate c that makes the left-hand side equals the limit from the left and the limit from the right, and the function value, they're all the same, only for c equals 2/3. And we went back and replaced it. This is guaranteed to be continuous everywhere. Continuous now on negative infinity to infinity, which means continuous everywhere, because we determined the appropriate c. And now that became continuous everywhere. Any questions for me? Any questions? Any questions? Okay, so let's talk about one theorem here. It's a very simple theorem. It's called the intermediate value theorem. It's extremely useful, however, and especially useful for chapter 4, when you'll see when. In chapter 4, we will learn, with the use of calculus, to solve any equation on the planet. Anything. We are very limited right now. We only can solve quadratic linear, maybe some polynomial functions that are factorable, radical, rational, but we will be able to solve any equation, but with the use of this theorem as well. This theorem will not give us the solution. Another theorem from chapter 4 will. This theorem only tells us where the solution is. It tells us where the solution exists, or whether a solution exists, or solutions exist, not finding them. Later on in chapter 4, we will be able to find them with as many digits accuracy as you want. Literally, with as many as you want. Okay, so what is this theorem all about? Suppose I have a function that does this. Do you think that f of x equals 0 has solutions or not? This is an equation. F of x equals 0. Does it have solutions or not? It does?
It does not.
Okay. Anyone else?
That's
Of course, it's right here. It crosses the x-axis. This is where I determine the x-intercept, or I find the zeros. In this case, the 0 of the function, right here. So, would you accept that this is a continuous function, the way I graphed it? Do you accept that, for example, on the interval a comma b, on the left-hand side, f of a is positive or negative?
negative.
Good. And would you accept that f of b is a positive number? And that's it. That's the whole theorem. And we're going to write it in a minute. So if I have a continuous function, this function, and on a particular interval, we like this interval to be 1 unit, not between 1 and 10, but between 1 and 2, or 2 and 3, or between -2 and -1, -1 and 0, 1 unit interval, or smaller, but not bigger than 1. So if I say to you, I have a continuous function, and on the interval 1 comma 2, on the left hand side, on f of 1 is negative and f of 2 is positive. That guarantees a solution between 1 and 2?